All right, we're going to continue our discussion about Lewis structure of polyatomic ions. So let's look at a couple of examples that's a little bit more complicated. Okay, let's say this one. All right, carbonate with -2 charge. Okay, so carbon has, so the same thing, we count total number of valence electron first. So is carbon is 4. Now keep in mind that we're counting valence electrons only, okay, not total number of electrons. So carbon has 4, oxygen has 6 times 3, right? There are 3 oxygens. -2 charge means this whole group of atoms somehow, okay, has gained 2 electrons, so +2. Okay, so in total you have 24 valence electrons. Now let's look at the layout of the atoms. Okay, so carbon in the middle, 3 oxygens, and then connecting all of them. Right, so make sure you keep doing the math. Okay, whenever you put something down here, putting in bonding or dots, okay, make sure you do the math here. So -6, 3 bonds, that's 18 left over. Again, surrounding atoms first. Okay, surrounding atoms first. Don't evenly distribute 18 to 4 atoms. Okay, you gotta make sure all oxygens with 4 pairs. So this oxygen has 1 pair, so put in 3 more pairs here. So is this oxygen needing 3 pairs? You can imagine this oxygen will also need 3 pairs. So by putting down 6, 6, 6, that's 6 by 3, it's 18. Oh, you have nothing left. So since you have nothing left, so this carbon won't be getting any dots. Now, at the end, you always want to double check, does everyone has 4 pairs? Does this oxygen has 4 pairs? Yes. Does this one? Yes, this oxygen as well. What of the carbon? Does this carbon has 4 pairs? Nope, it only has 3 pairs, 3 bonds, that's 3 pairs, right? So we're gonna need to give this carbon more electrons. Well, we don't have any more. So this is when you need to induce the multiple bonds, either double bond or triple bond, okay? But the double bond or triple bond, they don't have to be symmetrical, okay? They don't have to be like 3 double bonds so it looks symmetrical. No, you actually don't. The carbon actually don't want 3 double bonds, because 3 double bonds, that's like 1, 2, 3, 4, 5, 6 pairs of electrons around the carbon. So the carbon does definitely don't want that, okay? So currently it has 3 pairs, okay? You only need 1 more pair, not 3 more pairs. So one of the lone pairs, since we don't have any more electrons, right? So we have to move one of the lone pair to becoming the bonding pair. So this will, let's redraw this, okay? It doesn't really matter which lone pair, okay? It doesn't even matter which oxygen, to be honest. So it has double bond with this carbon, and the other 2 single bonds are still gonna remain as single bond, okay? So this oxygen is losing one of the lone pairs, but still has 4 pairs, 1, 2, 3, 4. But the carbon in the middle has 1, 2, 3, 4 bonds, that's 4 pairs, okay? The other 2 oxygens are not changed. And it has -2 charge, so you need the square bracket, cover it up, okay? So what if you say, hey, I want to use different lone pairs. Let's say, you're gonna use different color, okay? What if I move this lone pair over, not that pair, okay? So this will lead to a slightly different looking Lewis structure. So instead of having double bond between these carbon oxygen, okay, this oxygen will keep its 3 pairs. So it's the other oxygen. The oxygen at the bottom will be having a double bond with the carbon. So this will be also a possible Lewis structure for this one. And what if you have a lone pair from this oxygen to come over? So that will lead to this green structure. So you can imagine the double bond will be between this carbon and this oxygen. Okay. So you can see there are 3 possible Lewis structures. The difference is the double bond location. The double bond located here or here, or towards the bottom. So these 3 Lewis structures are all existing. Okay, this is what we call the resonance structure. This is another excellent example showing you there are three possible structures equally contributing to the real structure. Okay, so this is the real structure of carbonate.